now we finally get to an example to solve a system of equations using this matrix method. Now, fair warning, this example is a little bit long. There's a lot of steps to it, a lot of algebra to do. But when we get to the end of it, we'll have seen a full-fledged system of equations problem. And then in the next lecture, we'll talk about some different examples that we can see and different ideas that come out of it. So stick with me throughout this example. It's a little bit long to get to the end, but once we do, we'll have our first example under our belts. So again, our general setup looks like this, where we have a system of two equations with two functions x1 and x2. They're coupled and autonomous, and our structure is x prime equals ax. So in this case, a is 2, -6, -1, 3. So just a matrix, 2 by 2 matrix of constants. And again, for all the problems we do, they're all going to be matrices like this with constants, and all that changes from one problem to the next is what the values of these constants are. But just as we saw with second order equations, changing those constants a little bit can dramatically change the kinds of solutions we get. So we'll take some looks at examples like that. So we go back, the key to finding these values of r, remember the assumption is that x equals e to the rt times u. So the goal is to find what r is, and then also once we do that, we need to find what u is. So we need to find these two pieces, r and u. And once we find those, we'll have our solutions, the solution to this system of equations. So to find r, we go back and say the key is that the determinant of a minus ri has to equal 0. So a minus ri is going to look like, if you take a, and along the diagonal here, we're going to subtract r. So that's what happens when you take ri, is you get, let's put this off to the side here. I, remember, is the matrix with 1s on the diagonal. So r times I would be ones that have r's here and 0s elsewhere. So if we're subtracting a minus ri, the entries in these two positions are going to have an r subtracted from them. The entries in the other positions will remain unchanged. So this will be true in every one of these examples you see. You'll get used to doing this. We're going to have 2 minus r here, -6 is unchanged, -1, and 3 minus r. And our goal is to take the determinant of this 2 by 2 matrix. So that's the setup. That's how we start every one of these problems. To find r is take your A matrix and then subtract r along the diagonal, the first diagonal, and then take the determinant of that. So just as a reminder from back when we did the Wronskian, the same idea holds here. To take the determinant, you take and multiply along this first diagonal, and then along the second diagonal, and then subtract in that order. So we're going to have 2 minus r times 3 minus r minus -6 times -1. Right, so here we have 1 and 2, and we're subtracting like that. So that's just the definition of the determinant, and that has to equal 0. So we're solving this equation where we're looking for what value of r makes that equal 0. And after one more step, you should see that this is just going to turn into a quadratic equation that we're solving. So again, it's reminiscent of what we did with second order equations, where a differential equation ultimately boiled down to a quadratic equation, the characteristic equation. The same thing is true here, and it's really for the same reason that a second order differential equation can be written as a system like this. So it's the same kind of concept, just in a new light, but otherwise it's not too unfamiliar. So once we have that done, we can expand this out. So this would be 6 minus 5r plus r squared minus 6 equals 0. Or cleaning it up a little bit, we'd have r squared minus 5r equals 0. So of course, to solve this, you could use the quadratic formula, but this one factors nicely. And we find that there are two values of r that work, 0 and 5. So in solving this system, we found the first part to our answer. We found r. Maybe I should label these something other than 1 and 2 to avoid confusion with the other parts. So we're looking for r, and then we're looking for u. So we found r. We found the two values of r that work, 0 and 5. And I'll write this down at the end, but there's a special name for these. They're called the eigenvalues of this system. And there are lots and lots of applications of eigenvalues, lots of applications where the same kind of setup takes place. And ultimately it comes down to when you're solving a system like this, you can approach it in the same way. You move things to one side and then factor out your vector, and you often end up with something like a minus ri equaling 0. So the values that you find by doing that are called these eigenvalues. In the next lecture, we'll talk more about what these eigenvalues tell us about the system and how we can recognize some features about the solution just by looking at the eigenvalues. But we'll leave that for next time. For now, we want to continue on with the problem. So here we've done part A, finding the eigenvalues r, 0 and 5. So now we have to go find u, and what's going to happen, what we're going to find is that we have two values of r that satisfy this equation. And each value of r is going to have a vector u that goes with it. So we have two values of r, two eigenvalues. We're going to have two vectors, and each vector is going to go with one of them. So we're going to have two eigenvalues and two eigenvectors, and they're kind of matched pairs. So one value of r is going to have a u vector that goes with it, its eigenvector, and another value of r is going to have a different eigenvector, a different value of u. So to find u, we're going to go back to where we had u defined in this equation. Remember, this was the setup earlier, that a minus ri times u equals 0. So that's kind of this other piece, well, earlier in the example, but that a minus ri times u has to equal the 0 vector. So what we're going to do is look at the two different values of r. So let's assume for a second, let's take the first value of r. If r equals 0, then a minus ri, remember the A matrix was 2, negative 6, negative 1, and 3. So a minus ri is this right here. So if r is 0, we'd have 2 minus 0, then negative 6, negative 1, and 3 minus 0. If we take the eigenvalue 5, we would set up the same thing but use 5 for r instead. So we'll do that a little bit later, but we'll start with the first value of r of 0. So that's a minus ri, and then times this vector u, so it's going to have u1 and u2 as these two constants that are unknown to this point, and that has to equal the 0 vector, right? So simplifying a little bit, we get 2, negative 6, negative 1, 3, u1, u2 equals 0, 0, which is really just a system of equations we need to solve with unknown constants u1 and u2. Again, you know how to solve systems of equations, and so you can use some of that here. But it turns out there's some interesting features here. So first of all, note that this system of equations, well, let me write it down first. In more familiar form, we could write 2u1 minus 6u2 equals 0, negative u1 plus 3u2 equals 0, right? And so you could solve this by substitution or elimination and so on. But it's actually a little bit simpler than that, because I don't know if you've noticed, but these two equations are linearly independent, or linearly dependent, I'm sorry. In other words, if you multiply the first equation by negative 1/2, for instance, you get the second one. Or you can multiply the bottom one by negative 2 to get the top one. They're linearly dependent, which means if you try to do elimination, for instance, if you do that, you won't be able to get a solution in the way that you're used to getting a solution. So it won't be kind of as familiar. Now, this may sound like a roadblock, but it turns out this is entirely expected, right? So this is no surprise, or shouldn't be a surprise, really. The idea, the reason this is happening, the reason that we shouldn't be surprised by this, is because we built this system of equations by setting a determinant equal to 0. Which, if you remember, that's how we tested linear independence or dependence using the Wronskian. So it all comes back to that, so it's not terribly surprising. So every one of these examples that you do, you're going to run into this, this issue where the two equations are linearly dependent. Now, what that means is that there's not a unique solution, U1 and U2, that makes this happen. And so what you can do is you can pick any value you want for one of them and then find the corresponding value for the other. So it's a little quirky the first time you see it, to have that freedom of, well, I can take anything I want. The idea is, since they're linearly dependent, if you try to do elimination, for instance, you'll find that there are infinitely many solutions to this. And specifically for any value of U1, there's a corresponding value of U2, or for any value of U2, there's a corresponding value of U1. So once you pick a value for one of them, there's exactly one answer for the other one, but you can pick any value you like for one of them. So that's a piece that can trip you up early on when you see this, but it's actually nice for us as we actually get to solve problems, because it makes life pretty easy when you get down to it. So because they're linearly dependent, there are infinitely many solutions. So for example, each U2 has a matching value of U1. So what we do, just to make life easy, is we pick a value for one of them. And as long as we pick a non-zero value for one of them, then it'll give us a realistic solution. So what we're going to do is we're just going to let U2 equal 1. That's kind of the decision we make to pick this in such a way that it has sort of a consistent pattern to it. What this looks like is, if you take that first equation where you have 2u1 minus 6u2 equals 0, basically you get u1 equals 3u2. And then in the bottom equation, if you do the same thing, where you have negative u1 plus 3u2 equals 0, if you solve that one, you'd also get u1 equals 3u2. So again, that's kind of why you can't approach it the way you used to with substitution or elimination, because the information we gather is just this piece here, which doesn't lead to a unique solution. So any value of u2 will give us a solution. So all we do is we pick a value u2. So what we can write is we can write something like this. U2 doesn't have a specific value assigned to it. And then U1 is just 3 times U2, whatever it is. So then we just decide to let U2 equal 1. which just makes this vector equal 3, 1. So that's probably one of the hardest parts to kind of get your head around at first, that we get to just decide on a value. But the whole reason for this is that these equations are linearly dependent. Because of that specific feature, there are infinitely many solutions, and we don't get a unique solution, but instead we get, for any value we pick for u2, we get a matching value for u1. Notice we could have also picked a value for u1 and then found u2 based on it. It really doesn't matter much one way or the other. Just for consistency, though, I'll tend to do this, pick u2 equal to 1, and then find the vector u1, u2, just like this. So again, there's a lot of details going on here, but basically it boils down to you set up this first determinant to find r, and then once you do, you pick one of the values of r. In this case, we started with 0. You go back to this point where you have u to solve for, and then it quickly reduces down to a system of equations. They're going to be linearly dependent. So all you need to do is pick a value for either u1 or u2. Again, I'll let u2 equal 1, and then solve for u1, and whatever multiple of u2 that is goes here, and then you have a 1 here. So that's the general format that we'll follow. Again, you could find a different eigenvector that goes with it, but it would turn out to just be a multiple of this one. So as far as vectors go, it wouldn't change it much because it's pointing in the same direction. And that's kind of the significant piece with these vectors, is what direction they're pointing in. So this eigenvector 3, 1 would look something like this. It would kind of be pointed in that direction, like so. And we'll talk more about what these eigenvectors represent with the system in the next lecture. So with r equals 0, we get this answer for u. If we do the same thing with r equals 5, we'll get a second vector for u. So now we have, again, a minus ri times u equals 0. So we'd have now 2 minus 5 instead of 2 minus 0, negative 6, negative 1, and 3 minus 5. Again, u1 and u2. And so maybe to write this in more familiar form, the 2 minus 5 is negative 3. So you'd have negative 3 u1 minus 6 u2 equals 0. And negative u1 minus 2 u2 equals 0. Again, these are linearly dependent, just like we expected. So we do the same trick. We let u2 equal 1, and then we take either one of these equations and solve for u1. So u1 would be negative 2 u2. So our vector u1, u2 looks like negative 2 times u2, and we're letting u2 equal 1, and 1 times u2. So in the same logic, we get this vector. So just to kind of summarize where we're at so far. So first of all, we wanted to find r, and then we wanted to find u. So we found two values for r. We found r equals 0, and we found r equals 5. With r equals 0, we found a vector u, which was 3, 1. And with r equals 5, we found another vector u, which was negative 2, 1. And so for each eigenvalue r, we had a matching eigenvector u. So again, these are called the eigenvalues. And that eigen comes from the German for self. So the reason for this, without going into too much detail, is basically we're solving a vector equation that has the vector x twice, and so we're solving for the values that sort of lead to this self solution. So the eigen part, the eigenvalues, or the self, the values that relate to itself, and then the eigenvectors match with them. So each eigenvalue has one corresponding eigenvector. Now, putting this all together, wrapping it up, we're basically done. We've started with this assumption that the solution looked like this, and then we had to find the values of r and u that went with it. So once we've done that, we can go back and put it all together. So if x looks like this, basically we have these vectors that include two values. So basically, again, we're going to have two solutions. And x will be the linear combination of them. Again, kind of similar to what we did with second order equations. We get two solutions, and the reason for that is we have two values of r. So we have two solutions that fit this form because we have two values of r, and each of them has a corresponding u. So at the end of all this, x, the solution, is going to look like c1 times e to the 0t times 3, 1. So that's the first solution, where r is 0 and u is 3, 1. Then the second solution has r equal 5 and u equal -2, 1. So simplifying a little more, the solution looks like c1 times 3, 1 plus c2 e to the 5t times -2, 1. So there's the solution to our system of equations. We could also write this as x1 equals the first row of that. So that would be 3c1 minus 2c2 e to the 5t. And x2 equals c1 plus c2 e to the 5t. So there's our solution set. And if we're given initial conditions, we can solve for c1 and c2. But as it is, there's our general solution to the system of equations. So let's say, for example, we were given initial conditions. So this would look like the vector x of 0. In other words, x1 of 0 and x2 of 0 would be 0, -5. So in other words, this would be, if we were given the initial conditions, x1 of 0 equals 0, x2 of 0 equals -5. So we could just plug these in like we're used to. In the first equation, we'd have 3c1 minus 2c2 e to the 0 equals 0. In the second equation, we'd have c1 plus c2 e to the 0 equals -5, which reduces down to 3c1 minus 2c2 equals 0, c1 plus c2 equals -5. Again, a system of equations that you can solve, and I won't take the time to do it, but what you would find is that c1 equals -2 and c2 equals -3. Which means that our solution now, our final solution with specific values for c1 and c2, we have -2 times the vector 3, 1 minus 3 e to the 5t times the vector -2, 1. And again, you can write it as a system of solutions. You could write the two solutions down individually like we have up here, or you can write it down as a matrix setup. Either way is fine. I'm not going to be picky one way or the other. So again, I promised that this would be a long example, and it was, but once you get the hang of this, it's not too hard, because all you have to do to find your solutions is find the values of r, the eigenvalues, which you do by solving this, setting up this determinant and solving the resulting quadratic. So it's just a quick, essentially quadratic equation to solve. And what we're going to talk about in the next lecture is the kinds of solutions you can get here. So of course you can get, as we did, 2 distinct real solutions. You could get 1 repeated real solution, or you could get complex solutions. So there's a variety of options for that. And those are going to control the behavior of the solution, just like we saw with the second order equations. Then finding the eigenvectors, you pick one eigenvalue at a time, and you go back and solve this equation. And again, every time you do this, you're going to get a linearly dependent system of equations. So you just pick, let u2 equal 1, and then find u1 as a constant times that u2. So that gives you your eigenvector in each case. And then once you have that, those two values of r and u give you your 2 solutions of this form, and the final solution is the linear combination of them. So there's a lot of ideas here that are very reminiscent of what we saw with second order equations, especially homogeneous ones, because all the ones we're doing here are homogeneous. So a lot of new stuff, but really it ties back to stuff that we're familiar with from the past. So in the next lecture, we'll talk about some different kinds of solutions you can see based on the changing values in this coefficient matrix A.